Traditionally, geometric data such as terrains have always been stored locally. The remote access presents characteristics of a combination of data serving like files and real-time streaming media. In this sketch, we present a client-server streaming terrain rendering system to serve and stream large terrains to heterogeneous clients. The process is sensitive to both the client's capabilities and network bandwidth. Streaming allows us to have dynamic virtual worlds in which multiple users could collaborate at the same time. The basic requirement of a geometry streaming system is achieve user experience akin to local rendering. A single server serves multiple clients of different profiles using the same content repository. This repository could change with time. New content may be added or removed at will. The system must adapt the quality of transmitted data based on client and network characteristics. The typical requirements of a streaming system are to achieve interactive frame rates, high quality rendering, immunity from changes in latency. We utilize a combination of LOD, client-side visibility culling, server-side visibility detection, speculative prefetching with caching, as well as geometry compression techniques. The system ensures minimum server response time. Terrains can easily be divided into tiles. These tiles may be efficiently compressed using standard image compression techniques. They may be tessellated at the client end into the final rendered mesh. We may individually stream these tiles depending upon need. The server sends a collection of tiles to the client depending upon the potentially visible regions of the terrain based on viewer position. We aggressively utilize level of detail to reduce the amount of data to be transmitted to the client. The transmitted resolution of the tiles is directly dependent on the client capabilities and also the available network bandwidth. The utilized bandwidth between the server and the client is monitored at regular intervals to select the optimal representation to be transferred. For sending a higher level of detail, we only need to transmit the difference between the super-sampled lower level tile and the actual tile to be transmitted. We compress this resulting residue using the extremely efficient PTC image codec. The server maintains a large number of pre-computed levels of detail for the terrain, which may be transmitted when demanded. Using multiple levels of detail also allows us to have a higher level of performance at the client end. To reduce the amount of data to be transmitted to the client, we prefetch sections of the environment that might potentially come into view in the near future. We use motion prediction to estimate the position of the viewer and then request the sections of the environment in advance. Prediction allows us to avoid the effects of changing latencies. It also avoids popping artifacts that might be visible otherwise if tiles were to be displayed only when they came into view. Caching also helps in avoiding retransmission of data. We use an extremely efficient LPV scheme that expunges tiles from the cache based upon their potential visibility considering the current direction of motion. These methods allow us to significantly reduce the amount of transmitted data. The system allows dynamic objects to be introduced into the virtual environment. Dynamic entities are a hard problem, as a server must continuously monitor the state of all dynamic entities in the virtual environment. We use a method of lazy updation for dynamic objects where the client only downloads the model when it is actually visible in its viewing frustum. Any changes to the environment by the client is immediately notified to the server, which then relays the information to all connected clients. Other clients may then download change objects at will. Our system allows us to incorporate user-defined annotations to the terrain. These annotations are sent to the server immediately after being added. The server updates its terrain database accordingly. Multiple levels of user permissions may be added for the annotations. Such techniques are especially useful for community-based mapping applications. We presented the design and implementation of a terrain streaming server. Such a system is suitable when multiple users need access to a large dynamic environment residing at a central location. A terrain streaming system such as this would be extremely useful in collaborative 3D mapping applications, massively multiplayer games with completely dynamic environments, and also for serving low memory footprint devices such as PDAs. We conclude by demonstrating a few other capabilities of our system.